Hello everybody, my name is Shiva Tejesh, and in this video I'm going to explain about the correlation of two-dimensional signals. First, we'll discuss about the basic definition of correlation, followed by the correlation of one-dimensional and two-dimensional signals. Then, we will also discuss about the applications of correlations in image processing with the help of an example using MATLAB code. Correlation is defined as a measure of similarity between two functions or signals or waveforms. There are two types of correlations, cross-correlation and autocorrelation. We are going to discuss mainly about cross-correlation in this video. Cross-correlation is the correlation of two different signals, whereas autocorrelation is the correlation of a signal with itself. Now, let us discuss about the cross-correlation of one-dimensional signals. The cross-correlation between two one-dimensional signals is defined as the measure of similarity or coherence between one signal and the time-delayed version of another signal. The cross-correlation can also be called the degree of relatedness between one signal and the time-delayed version of another signal. Consider two complex signals x1 of t and x2 of t having finite energy. Then the cross-correlation of these two energy signals is given by the formula r of tau is equal to integral minus infinity to infinity x1 of t multiplied by the conjugate of x2 of t minus tau dt. If the two signals are real, then the cross correlation between them is r of tau is equal to integral minus infinity to infinity x2 of t minus tau into x1 of t dt, or r of tau is equal to integral of minus infinity to infinity x1 of t plus tau x2 of t dt. If the energy signals x1 and x2 have some similarity, then the cross correlation r of tau between them will have some finite value over the range of tau. The variable tau is called the delay parameter or searching parameter or the scanning parameter. The time delay parameter is the time delay or time shift of one of the two signals. This delay parameter determines the correlation between the two signals. Correlation of two-dimensional signals. Generally, a two-dimensional function is used to represent an image with the variables representing x and y coordinates, and the value of the function at each value of an x and y gives the intensity of the image at that point. The mathematical formula for correlation between two-dimensional signals is as given below. W of x comma y correlated with f of x comma y gives sigma s is equal to minus a to a, sigma t is equal to minus b to b, w of x comma y multiplied by f of x plus s comma y plus t, where w of x comma y is an m cross n filter and a is equal to m minus 1 by 2 and b is equal to n minus 1 by 2. 2D or image correlation can not only be done by using the mathematical operation discussed before, but it can also be done with the help of matrices. The given image shows the step-by-step process by which image correlation can be done. We will now discuss the procedure by which the correlation operation can be performed on two-dimensional signals. Now, let us discuss the procedure to perform correlation operation on two-dimensional signals using the matrix method. Let us consider two matrices M1 and M2, where M1 is a 5 by 5 matrix and M2 is a 3 by 3 matrix. The size of the cross correlation product of M1 and M2 is a 7 by 7 matrix. In terms of lags, the resultant matrix C is given as follows. The first step which we need to follow in order to perform correlation of a two-dimensional signal in matrix form is to pad the matrix M1 such that it becomes a 7 by 7 matrix. After that, we line up the two matrices M1 and M2 such that their 1, 1 elements coincide. This placement corresponds to C0, 0 in the output matrix. To find C0, 2, we slide M2 two rows to the right. After performing the previous step, now M2 is on top of the matrix M1. We then compute the element by element products, and add them together in order to obtain the element C0, 2, which is given by the equation and results in 585. The same process is repeated for all the elements of the matrix M1. This will give us the result of the correlation between the matrices M1 and M2. Let us look at a practical example of how correlation can be applied in image processing. In this example, our main objective will be to correlate an image with a section of itself and observe the correlation graph. The given MATLAB code is used to load a grayscale image and display it to the user. After loading the input, our next step is to select a portion of the original image which has to be cropped out and then correlated with the input image. As we can see, we have selected a rectangular section of the image and displayed the image after cropping it out. Now, we use the MATLAB function xcore2, which is used to find the correlation between two-dimensional signals, to find where the smaller image fits the larger image, that is, where the section of the image fits the input signal. The maximum of the cross correlation corresponds to the estimated location of the lower right corner of the image. The int2sub function is used to convert the one-dimensional location of the maximum into two-dimensional coordinates. After plotting the graph of the correlation of the two images, now we have to reconstruct the original image from the two images which we have correlated. The smaller image is now placed into the larger image after rotating it by 90 degrees as per the MATLAB conventions. After which, the smaller cross section of the image is highlighted by drawing a red rectangle around it, as we can see in the image given below. Now, let us briefly recall all the concepts which we have discussed in this video. In this video, we have discussed the correlation of signals and the procedure to calculate the correlation of both one-dimensional and two-dimensional signals, and also the applications of correlations in image processing. We have also practically demonstrated the correlation of an image and its section with the help of MATLAB. Hope you enjoyed this video. Thank you.